Try in half an hour to explain you how we go from basic science or big science to be able to complete a big program. And in fact, what you will see is that you need a lot of technology, and to be able to set and to make this technology work, you need a lot of engineering. So this is the outline of my talk. So a few words about the basic ideas. What is the purpose of this big fusion facility? Then a few words about the laser baseline to understand what it is made of. The next point is that before you build a huge facility, you have to go prototyping, because you have to check every basic ideas you put at the very beginning are working. And then a few slides to explain what we learned from this huge program. So at the very beginning, there are three basic ideas coming from the science. The first one is related to this gentleman that we talked already during the morning, and this gentleman is Theodor Maiman, and this is his discovery, the one he made in 1960. It is a ruby laser. So this is the size of the laser he built in the 60s, and in the background what you can see is a few beam lines of this, I would say, old US facility that was called NOVA. Now you need something else. In order to be able to go to fusion experiments, you need neutrons. And the first experiment to create neutrons with a laser was made in France in 1969, so roughly 9 years after the discovery of laser. And then in 1972 there was a gentleman, John Lackers, working in Livermore, that explained how to proceed to be able to compress the matter and go to some conditions where it is possible to create a fusion in the laboratory. The next step is to build a facility, and this is roughly what we built in France. We call laser mégajoule. This was decided when we stopped, I would say, nuclear testing in the Pacific Ocean. And then we decided to build a facility in order to be able to study and to create fusion in the lab. The trouble is that for doing such, you have to create such kind of plasma as the one you could find in the sun. The trouble is that the temperature range should be in the million of degrees, pressure 1,000 of bars, and the time range is only a few billions of seconds. Roughly it's 100 picosecond. So it's quite difficult, and for doing such, the best idea is to start from a laser. The basic principle is to be able to mix two types of fuel. One is the basic deuterium, which is the first isotope of hydrogen, and the second one is tritium. If you can mix them and create conditions such that you create fusion, then you get neutrons, 14 MeV neutrons, and then you get alpha particles, roughly 3.5 MeV. So this very basic and simple equation is the one everybody's trying to fulfill in fusion reactors. So currently there are two ways. One way is related to this big machine, which is a tokamak facility. This is the design of the huge one that is currently being built in France, ITER. And the second one is this kind, laser mégajoule, where you can see the target chamber, and inside we put the pellet. So there are differences. Differences are coming from the basic idea. In fact, we have to be able to confine the system such we create the conditions to get the neutrons and the alpha particles. Temperature should be in the range of 100 million Kelvin, but then we know that the product of the density times the confinement times should be something around 10 to the 14 second per cubic centimeter. And then you get two ranges. The first one is the case of the magnetic confinement, where the density is quite low. It's quite low because then the deuterium tritium is in something that is roughly 800 cubic meters. And then you need to have a very long time to be able to sustain, I would say, this phenomenon. This is almost stationary. Why? Because plasma, I would say plasma is reacting roughly in the picosecond range. The second solution, so this is mainly devoted for, I would say, civil applications. The second range is this one, in which, in fact, in order to decrease this time to a few nanoseconds, which is the case of lasers, then you have to increase the density. This is almost the density of a solid, but this is something you can get if you have a very high temperature, a very high pressure. And then the difference is that for sustaining the system, then you need only a few nanoseconds. So the idea is to fill a box. It's like an O1. We call it an all-home. It's an open chamber with two holes in which you are able to send the beams. And roughly the quantity you want to put into your small all-home is 2 megajoules. This is roughly the quantity of energy that you would put inside. So there are many beams coming from both sides. They get inside, and inside what you put is a small pellet. And in this pellet there is a very small amount of fuel, a mix of deuterium tritium, roughly less than 1 milligram. And in order to be able, as close as possible to the solid density, the best idea is to start with a very low temperature. So you start with something that is quite close to the triple point of this fuel mix, and then you have already the solid density. So far, it seems quite surprising that for being able to reach 100 million of Kelvin, we are starting with something that is quite cold. Then you have to do experiments in order to be able to reproduce what is going on in the sun, which is creating the reaction we call ignition, and then trying to find the best condition to burn the fuel such you can release energy. Of course, the idea is to release much more energy than you put in the system. The system is designed such you should be able to release 10 times more energy that you put in the system. So what is expected is roughly 20 megajoule of energy. So when you look at those conditions, it's clear you cannot build only one laser with one beamline. You have to find a laser or an architecture with many beamlines. Then there are many other reasons why you should do so, because if you put only one beamline, you would not get symmetry. In fact, the idea is that those many beamlines you would put into your small all-home will create some X-rays, and then the X-rays will compress the capsules. On the other hand, it's quite difficult to build such a big laser because it was shown, I would say, during the 70s that over 1 meter optical components are so expensive it doesn't make any sense. And then the decision was to build something that would be 1 meter square but split into small parts, and roughly the size of one beam should not exceed half a meter by half a meter. Then the idea is to build something where you get finally the order of 200 beams, and this is related to the fact that there are many different bundles you will put into your target such that you can illuminate the best, or I would say with the best homogeneity. So everything started in Rochester in Omega in the US in the 80s. This laser is made of 60 beams, but it's only providing 30 kilojoules. 30 kilojoules is quite small. Then there was the US program in Livermore that is called NIF, National Ignition Facility, who started operating in 2009. And at the same time, the same program started in France, and we are currently, I would say, providing or finishing the few beams to be able to be up to the full power in 2018. At the same time, as I told you, there is this civilian program, ITER, that should be ready by 2035. So in fact, this facility was built near Bordeaux, so south of Bordeaux, which is on the coast close to the Spanish border in France. And this is built by a national program at CIE. CIE is the French Atomic Energy Commission. So the basic idea is to start with a very small laser source, then to be able to amplify to something that is almost, I would say, custom, off the shelf or commercially available, then to build big amplifiers, because then we think about 20 kilojoule, and then to go to a different wavelengths. The idea is coming because we are using glass doped with neodymium. This is the only available material you can get in very large dimensions. So the main laser is working at, I would say, 1053 nanometers. Then it has to be converted to UV light. Only reason is that UV light is much more efficient to be absorbed in the fuel. So it's converted with KDP crystals, and then it's focused. So it's relying on two basic ideas. First, you have to have large components, and then you have to have many beams in order to be able to provide your 2 megajoule onto the target. So everything is started from a very small system that is roughly a few meters long. Then it's going to a main laser that is roughly 100 meters long. You have then to transport the beam to the target chamber. You have to focus, or you have to frequency convert to UV light, and of course you have to focus to the target chamber. So the idea is to start with two big amplifiers, like a huge cavity. Then you will send the light in, and then you will propagate, I would say, one way, second way, third, and fourth. The idea is to remove all the energy that is stored in the cavity, such that at the end you remove all available energy. This is 100 meters long, and this takes roughly 500 nanoseconds. Then this huge amount of energy you transport to the location where you have your frequency converters, and then you frequency convert to UV, and then you focus onto the target. So this is the basic idea, and I will show you a small movie. Wow. So sorry, my check is not good enough. So I will skip it. So everything is starting in a small part that we call the front end, and it's in fact located into a very small part of the laser. It's a ring fiber oscillator, and then the laser itself is fiber coupled to this conventional or type of conventional laser that will provide roughly 1 joule, and this is roughly what will be put onto the main laser. It has many different types of, I would say, features. The first one is that we should be able to provide exactly the pulse shape that is required to perform the experiments. There is some kind of long foot, and then there is some increases with some, I would say, particular or specific times where you have to create something such the energy is increasing. The second point is that we create square beams, and then square beams are propagated inside the main amplifier. The only reason is that it's cheaper and it's more convenient to create square or rectangular components, while from, I would say, an historical point of view, most optical components were using round beams. At the same time, there is spectral shaping, and everything is starting with very conventional components. Then it's increased such that we are using 1 meter long slab amplifier that is pumped with flash lamp in order to provide a very large beam that is roughly 40 by 40 square centimeter. And this is made in such a big, I would say, unique type component in which you have slabs that are stacked together. This one is a fake one, so there are only 3. And the idea is to be able to pump and to create, I would say, laser beam conditions for 8 beams at once. So there was some very important engineering design such we can minimize the cost and make it quite cheap. The second point is that in such a large amplifier, the quantity or the stored energy is quite huge, 4 kilojoule, and the extraction is roughly 1.5 kilojoule, which is quite good. Another thing is that, in fact, the gain is quite small, which means that if you get 1 coming from the left, then you get 1.28 when you have extracted everything. It looks like the gain is quite small, but in fact the reason is that it is made this way, 8 beams at the same time, and there are 2 amplifiers. In each amplifier you get 9 slabs, and you go 4 times in each, which means that at the end the total gain is 1.28 at the power times 4 times 942, which is 72, so the gain is quite high, and this is the reason why the extracted energy is so high. At the same time, you see, because we are using large components, you have to have a lot of additional mechanical part and technology to be able to use them, clean them, and install them. Of course, everything is made in clean rooms, and there are many different types of, I would say, additional handling equipments you need to have to be able to build your laser. Everything is starting from, of course, the grid, then going to the capacitor banks. You store the energy, and then the energy is sent to the flash lamps, roughly in some 500 microsecond pulse, and then, of course, sending the light to the amplifiers. Finally, at the end, you have to create UV light from infrared light. This is done with 2 kDp. So the first time, or at first, from the infrared light, you will create green, but not too much, such that you have enough infrared. And then in the second crystal, you will mix both, and you will create the UV light. This is made with this kind of crystal. It is the way it's growing. It's fully natural. It's not polished. It's exactly how it is going out of the furnace. Then another thing that was made is that we don't focus with lenses. We focus with gratings in order to get a very nice focal spot. This is an example of the focal spot that was obtained on the prototype. It's roughly less than 700 micrometers. And as you can see, the profile is very, very nice. On top, you get something that is in a range of 10 to the 15 watt per square centimeter. So I said, in fact, we don't focus with lenses, we focus with gratings because it has 2 functions. First, you get remaining light from infrared and green, and you just want to focus the UV. This you can do. So then the infrared and the green are going through to some kind of beam dump, and then only focused is the UV light. This is the first idea. The second idea is because we are using 8 beams from 1 amplifier, then 4 beams are focused at once. So it means, in fact, each of those gratings is just one subaperture of a large one, and they are recording such that, in fact, the focal spot is exactly there. In fact, when you look at the focal spot, you don't see anything inside. There is some kind of, I would say, structure, but you don't see the overlap. It's quite perfect. And this is coming only from the basic idea that is to record the 4 gratings at once. So the next point, of course, is to create a prototype, which we did in 97, and then it was finished in 2001. And it was possible to show in 2003 that on one beam, we can get what was expected. We got much better. We were thinking 7.5 kilojoule, but then we got 9.5. When we did that, we learned from the US that they were able to achieve 11 kilojoule. So the question was, do we go to higher energy or do we stop? And then we decided to stop. Something else I didn't tell you is that the laser is able to shoot every day. In fact, once a day, it's enough for doing experiments. And then after 1,000, in fact, we did 1,500 shots. You can have some background and you have enough feedback to go to the LMJ design. Something very important is that because you plan to build a huge facility, then you have to reduce the cost. And during the engineering design, it's better to think how to reduce the mechanical parts, how to reduce the cost. And so the idea is coming from this principle. It's a cassette. In fact, we call it a line replaceable unit. It's something you can put in the laser and you can remove, so you can have spare parts and you can change everything very quickly. And then the second principle is that for doing that, in fact, the laser is supported by a frame and everything is provided inside the laser from the bottom. So you have different types of, I would say, components. One thing you can see is that everything is square. So the conventional idea of a disc and round beams, there is no trouble. You can create square components, you can fit them into mounts, and everything is possible. Something that you realize is when going to the far field, which is when you're focusing at the pinhole location, then the beam is round and it can go through some very classical pinholes. So you have the 2 main amplifiers, and then in order to have a very nice and plain wavefront, there are very long distances for telescopes such that the beam can propagate as, I would say, a perfect plane wave. So this is roughly 50 meters, this is 20 meters, so in that case the focal length of the lenses were 25 meters. So now when you go to the next, which is the full facility, LMJ, you go to, I would say, industry, and then you ask the people to just duplicate what you did. So this was one prototype, and then you build 30 of them. Of course, you have a huge building, and then it was decided to surround the main target chamber with all the beam lines that then will be concentrated to the target. Then you go to the building. This is how it started in 2003, in fact, and it was finished in 2009, but then you need a lot of time to put the technology inside. Almost, I would say, all equipment were finished in 2012, but then you need additional years to build everything, and you see, only after 2 years, finally, CA has been able to fire the first 8 beams in November 2014, and then you need roughly 4 more years to be able to complete everything. At the beginning, I said 240 beams. Then we have decided to go only 160. The reason why it is because it's so expensive that the French government has decided to delay a little bit, I would say, the delivery of the beams. So this is a huge building, roughly 100 meter. It's 300 meter long, and it's in the ground because in this location there is a lot of sand. The French people, they said that the Tour Eiffel could fit inside the building, so it is something that is quite huge. Now I have a few slides to show you how we install the system. So it's made of 4 laser holes. At the very beginning they are empty, they are cleaned, then they are painted, and then you start installing the technology. At first you have to have everything okay, so air conditioning system is working, and then it's a clean room. Then you move to install the technology, so all the frames on which you will put, I would say the package, because it's under vacuum or it's under clean atmosphere, and then all these boxes in order to fit the beam lines. You see the different beam lines here. You see 8 at each type of bundle. Then you have to connect everything to the vacuum equipment. Then I would say upper part of the structure in order to connect the fluids, the air conditioning system, the cool system, the water, everything you need to be operate the facility. So at the end it looks like this. There are a lot of connections. At the same time, you need to know where are your components, so you have to put fiducials and references everywhere in the wall, on the columns, and of course on each of the critical parts of your facility, so you know where are your components, and you have to align all those components such that the beam, of course, is propagating the right way. Another thing I didn't tell you, but it's related to the cassette system, is that everything is fully automatic, so nobody will be trying to put or remove components. There is some kind of automatic cart that is clean room in which you have the cassette, so it will be traveling under the under the laser beam lines, and it will be able to put and remove the components at the right location. So there is a huge and very long engineering program that has been made such everything at the end is completely and fully automatic. Okay, so this is how it looks like once everything is put in place. So this is one of the laser holes. Then, of course, you have to deal with the target chamber and with the diagnostics. So the basic idea is that you will get a huge target chamber. You will be able to provide all the beams from both sides, from the top and from the bottom. And then in the equatorial plane, you will get all the diagnostics. The idea is that when you do maintenance or when you want to repair, everything is out of the chamber. So in fact, diagnostics, I would say target holder, and everything you need to do your experiments are retracted in some kind of additional target chamber, so that the target is, the chamber is completely empty, and during experiment, everything is pushed inside. The diameter is 10 meters, and this is made of aluminum. This is put on some kind of huge stand, such that it's located right, I would say, to the laser beam lines himself. And for some purpose of radiation shielding, there are 3 different walls to prevent neutrons to escape or any kind of particle to escape from the building itself. For example, on this picture, you see those blue and green are the 4 beams going to the chamber, and some additional diagnostics that will be located along for observation. This is, for example, the neutron scattering system, and these are additional X-ray diagnostics. So the idea was to build the building just to keep a small hole in the roof and then prepare the target chamber in another building and then to put with a huge crane to put the target chamber inside the building. So the target chamber is made of aluminum. It's roughly 100 tons, and then it was put in place, and then it was covered with special concrete, 40 centimeters of concrete to stop the neutrons. Then it's put on the stand, and then additional structures are built all around to support all these equipment. The square aperture is for the beams, and the round aperture are for the additional diagnostics. Okay, so few slides, I'm finished. So just a few slides to tell you what we learned. First thing is that it's possible to go into research and development, and then because, or thanks to those kind of program, it's possible to develop technology. For example, growing crystals, these sides, being able to provide large optical components. This is, for example, a grading for compressors. Building square components. This component, in fact, is a Pockels cells. This one, for example, or these two are deformable mirrors. So a huge amount of new technology has been developed thanks to these large programs. Second thing is that you can standardize your components and you can decide to have only, I would say, a few sets of different components, and because using cassettes, then you can go to the industry and you can ask suppliers to do the same all the time for very sophisticated components. Of course, there are many components, but the more you have components, the better it is to go to be able to standardize. Then it will take a long time. For example, if you check when we started the program, early design phase was 1995, and in fact, roughly 20 years after, we were able to shoot with the first beam. So there is a long time, and you have to do a lot of engineering. You cannot go once, it's almost impossible. You have to check your design, you have to change. Commissioning takes a long time, roughly 7 years, okay, etc., etc. The second thing is that you have to exchange with other programs. In fact, there was the same program in the US, we can call it the sister program. There were many, many concepts that were shared with the US. For example, what is unique is that we are using identical laser beam lines, and any of the French laser slab you can exchange with the US laser. They are fully compatible. Then there was many collaboration between the two teams, and many things we tested in France or in the US that were shared with these teams. And finally, the third one is that, yes, at the beginning you have basic science, then you do a lot of engineering, but you need management, you need organization, and in fact you need I would say project management. Project management, training of the manpower and the employees. You have to build such in accordance or in agreement with your breakdown structure in which everything is prepared and everything is associated to some tasks. Of course, you have to have quality management and ISO standards, a huge documentation, a full CAD 3D model, because you cannot share with suppliers, it's almost impossible. And of course, you don't have to forget operation and maintenance, which means that during the concept and during the early years, you have to think about how do I do to replace the components? How do I do to check my components are failing, etc., etc. That's it.